All right, guys. So today is going to be a pretty big topic. It's always there's always some students that run into difficulty, some students that just run through and are awesome at this stuff, like right away, without me going through. So with that being said, I've taken a lot of precautions going in here, and we're going to stretch this one out, do it a couple times, not just today and tomorrow, and move on. It's not how it's going to be. We'll probably stick with this all week, maybe even into next week. We'll find out. This is the major cornerstone block of really anything that you would do to go through and beyond in chemistry is stoichiometry. We do it all the time. It's day one in AP Chem. It's used in every single lab that I can really think of from here on out. So try to pay attention as best you can. It's a 3-step process. There's quite a bit in it. There's lots of little details that we've talked about before. It's really a good cornerstone, top piece to everything we've learned so far. So think of it that way, and go into it expecting to run into some questions here and there. And anytime you guys can unmute, ask that question, or send me an email, or whatever you need to do to get a hold of me. So with that being said, let's get started. If you have a set of paper with you, notes, that would be good to take on as well. I've got my iPad. Maybe you're listening to this on a different device and you've got your iPad with you. Take some notes along with it. That's our best bet. Oh, I got to click on my iPad, not my computer. Haha. Okay, so after today, this is what we're going to be able to do. We're going to be able to calculate mass of a substance used during a chemical reaction. Last week, we did mole to mole. And moles are a great unit to use when you're comparing two substances, but we never actually measure moles in the laboratory. We measure things with scales, by mass or by volume. Something a little bit more kinesthetic, or tactile, something you can actually hold in your hand. A mole isn't necessarily, what's the word? Intuitive. You don't exactly see one mole, but you can start to get a sense of how much is there by mass. So we're going to start with this problem. We're going to start with photosynthesis. We're all familiar with it. I was out back this weekend, and we're gardening. We're growing some tomatoes, some lettuce, some carrots. The peppers just started popping out of the ground. So this is the reaction that's occurring in each of those plants. It's taking in CO2 and water, and you're getting oxygen and glucose. And the glucose is what the plant will use to create all of that organic matter, the stems, the leaves, the eventual vegetables that we will eat from the garden, right? That's all starts as glucose. So it's made from this process of photosynthesis, where light takes carbon dioxide and water and combines the two. So here's my question that I would pose to you guys at first. If a tomato plant absorbs 100 grams of water, because obviously you have to water a garden for the stuff to grow, right? How much do we expect that plant to grow in grams? So if I put 100 grams of water on it, how much mass will the plant gain? Of course, there's a percentage of that water that doesn't actually go into the plant, but let's just assume that I've put more than 100 grams of water on there, and the percentage that the plant actually soaks in ends up being 100 grams. Well, at first, you might think, oh, hey, well, if it's 100 grams of water, it's got to be 100 grams for the plant, right? But there's some chemistry involved here, okay? Think of it this way. Why is it not 100 grams? What's going on in that reaction on top that makes it not 100? And hopefully you can see that not only is there the, I can grab my, I thought I had a laser pointer. I must not. That's okay. You can see that there's the water here, right, in the reactants, but there's also something else, carbon dioxide. Where does that plant get the carbon dioxide from? The air around it, right? So not only is it taking in the 100 grams of water, but it's also taking in the grams from the air in carbon dioxide that it's soaking in. So because there's CO2 there, we're going to grow a lot more than 100 actually, not less. And then you can see that there's the 6-to-1 mole ratio in there, right? So there's 6 water to 1 carbon. Does that mean that that's going to be somehow involved here? And it's not just going to be 100 divided by 6 because there's a 6 in front of the H2O. I can't use that mole ratio here. Why can I not use the mole ratio with the 100 grams of water? Grams is not moles, right? There's this thing called molar mass that we talked about before, right? Converting between grams and moles. That will change everything when it comes to this. So there's so much that goes into it that actually, if you actually do this problem, you're going to end up taking 100, dividing it by 18, dividing it by 6, and times it by 342. 18 is the molar mass of water, and 342 is that molar mass of the glucose, the C6H12O6. And that's how I get that 316. And we're going to walk through how to actually do one of these problems. But first, let's set up what's actually going on. And if you're taking notes, I've got a diagram here that you especially want, okay? So if we're going to convert between grams of something that we know and grams of something that we don't know in a problem, I'm going to follow this process right here. I'm going to take the grams of my known, whatever it is, so the 100 grams of water, say, right? What I'm going to do is I'm going to convert that to moles, because I can't do anything with the reaction without it being in moles. Because remember, those coefficients in front are the mole ratios, not gram ratios. It's not the same thing. You can't do that. So to get from grams to moles, I'm going to use molar mass. And if you remember how to find molar mass, that's going to your periodic table. For water, it's H2O. H is 1 gram per mole. Oxygen is 16 grams per mole. So 1 plus 1 plus 16, because there's 2 hydrogens, gives you 18. And that's where that 18 came from before. So we're going to go from grams to moles for the first step. The second step, we're going to go from moles known to moles unknown. And that's exactly what we did last week. That uses the mole ratio from the equation, those numbers in front of each of the substances in its balanced reaction. And notice how I kept those on the same level. That's our horizontal shift, right? Grams to moles, it's kind of a vertical shift. It's the first thing we need to do. Then we need to cut over to another substance. And now once I have moles of unknown, I can convert that to grams of the unknown. And notice how there's no arrow at the top. We can't go grams to grams easily. You could figure that out, but by figuring it out, you're actually solving the problem anyway. So we never actually do that. But we get molar mass. We use the molar mass of the unknown substance to get from moles to grams of that. So there's the molar mass from the known substance, the mole ratio from the balanced equation, and the molar mass from the unknown substance that we use to get from grams to grams. I can't go directly. It's kind of like back when we did the mole ratio or mole test, and we had grams, liters, and molecules. We always had to go through moles. For stoichiometry, we always have to go through moles, even when we're going from grams of one substance to grams of another substance. So if the visual is not hitting it for you, I've got these step-by-steps here. There's 3 steps. Step 1 is to convert grams to moles using the molar mass of the unknown. That's what MM stands for, molar mass. Step 2 is to convert moles of the known to the unknown using the mole ratio. And step 3 is to convert moles of unknown to grams using the molar mass of the unknown. So we use molar mass of the known, we use mole ratio, we use molar mass of the unknown, which is those 3 right in a row. Boom, boom, boom. Okay? So if you don't have that written down somewhere, I would pause it if you're watching the video. If you're on the live session, hopefully you've been writing that down. And if you need more time or you want to fill this in later, I'll post this video and this PowerPoint afterward. All right, so let's get down to the nitty-gritty. Here's what we're doing. This is a mass-to-mass calculation, not a mole-to-mole calculation, right? There's a difference between this and what we did last week. Because here, it tells me there's 15 grams of aluminum, right? And it says what mass of silver chloride will react with 15 grams of aluminum. So we know our reactants, in other words. We're going to be able to write an equation from this. The equation is aluminum plus silver chloride makes silver plus aluminum chloride. And you can see the single replacement reaction happening. You can see that silver is a +1 charge, so it's paired with 1 chlorine. Aluminum is a 3+ charge, so it's paired with 3 chlorines. So we end up with a reaction that's not balanced right away, but we can balance it, going through those steps that we did a few weeks ago, right? If I put a 3 in front of silver chloride and a 3 in front of silver, I get a balanced reaction. Remember, any blanks that are in there, right? There's a blank in front of Al and there's a blank in front of AlCl3. Those are going to be 1s. So, and I do know from the example that my known quantity is 15 grams of aluminum. Those 15 grams of aluminum are going to match up with some amount of my unknown, which is the grams of the silver chloride. I don't know how many grams of silver chloride it's going to use to pair up with the 15 grams of aluminum. To figure that out, I'm going to go through my 3-step process. Remember, moles are mass to moles, right? And then moles to moles, and then moles to mass again.